Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a boarding school for boys, where in addition to teaching physics, I've been the debate coach. A common way of teaching students to structure an argument is via claim, evidence, reasoning. The debate team uses this in their cases. It's an excellent way to communicate. The AP exam often encourages this very structure by first asking you to check a box to indicate your answer, then to justify your answer. To many of you, claim evidence reasoning brings back bad memories of your 7th grade math class. You knew the answer instantly because good, smart boys and girls always know the answer. And you knew that the teacher knew the answer, but your teacher marked you wrong. You need to show your work. What? Why? This is stupid. I really need to show you how I solve 7 minus x equals 3 for x. The answer's 4. Justify my answer? Because math and logic. Duh. All right, and this teachery obsession with showing your work extended through much of high school. Okay, the problems got harder, but you could still do them without laying out the reasoning step by step as if you were a stupid person. Teachers are so condescending. Except in physics, good, smart boys and girls aren't expected to know the answer. In fact, the teacher doesn't know the answer to a new physics problem. Really? I've been doing physics since 1990. When I saw today's free response question, I didn't know the answer. I figured it out. I started with facts of physics. I continued with an energy bar chart, and I came to a conclusion. I didn't do claim, evidence, reasoning. I did evidence, reasoning, claim. When my students do test corrections, they invariably get hung up on the right answer. They might convince themselves that the answer is, in this case, that the amplitude increases after the collision. Then they twist and turn facts and equations to show increasing amplitude. And they get more and more frustrated with me as I show them their incorrect logic. Eventually, they do get every logical step correct. And then they'll say, therefore, the amplitude increases. It never occurs to them that their conclusion itself might be wrong. My students are like the evil prosecutors on shows like Law and Order or Matlock. We know this person is guilty. How can we arrange the evidence to convince the jury of their guilt? That's not how it should work. You start with the evidence. Based on this information, who is more likely to have committed the crime? Perhaps if more lawyers and police officers were physics majors, our criminal justice systems might be improved, just like Matlock. So don't be the evil prosecutor. They grow out of this pretty quickly. Don't identify the murderer and then cook the evidence to frame them. Instead, on the AP exam, leave the checkboxes blank until you've written your justification. Then, only then, come to a conclusion and check the box to say who done it. Now to the physics. Here's what we have in mind. We're going to do the 2018 AP Physics 1 paragraph problem, which you can Google online if you haven't done it already. If you have done it already, please bring out your solutions and we can go over it together. If you want to go to @JacobsPhysics on Twitter, you can send me questions, stories, and comments, and I will go over those toward the end of today's lesson. Here we are with the original problem. We have an object going back and forth. We are going to drop a heavy object on this thing right in the middle, right at the equilibrium position, and we're going to be asked what happens. The first question, determine the numerical value of the ratio of the periods, the period when the object is oscillating by itself and the period when the object is oscillating with the mass on top. Well, that's pretty straightforward. We know the period of an object on a spring is 2 pi times the square root of the mass divided by the square root of the spring constant. The question itself is asking directly for a factor of change. So let's do that. The number 2 doesn't change. The number pi doesn't change, Mooney's rule of ones. The mass triples because we went from mass m to mass 3m. The spring constant doesn't change. The spring constant is a property of the spring. So the factor of change equals the square root of 3. If you said 1.7, that's good enough too. Is that right? Well, let's quickly do the experiment. Let's get this thing going. Let's check the period. by going from trough to trough or crest to crest. There we go. So that's 0.80 seconds to 2.0 seconds. So that is a period in this case of 2 minus 0.8 is 1.2 seconds is the initial period. The new period should be 1.7 times that. So I take my trusty calculator and I get something like 2.0 seconds. Is that correct? Let's try it. I'm going to put the heavy object on here. Restart. Try it again. Actually, I don't have to do that because I can just go to run 2 and we will go from, get rid of run 3, there to there, from 1.1 to 3.2 seconds. So 2.1 seconds, I predicted 2.2 seconds. Physics works, I'm happy with that. Or maybe I predicted 2.0 seconds and I got 2.1 seconds. Physics works, I'm happy with that. All right, that's the simple part. Let's go to the more exciting part now. Here's the figure. How does the amplitude of oscillation of the two-block system compare with the original amplitude? And here I have to do the collision where I drop this thing right at the equilibrium position. Once again, I'm not going to check a box and then justify it. I'm going to do the justification first and then come to a conclusion. It asks for a clear, coherent paragraph length response. We'll get to that. I'm going to show you some paragraph responses, but first I'm going to show you the physics. I'm going to start with 3 wrong solutions, the 3 most common approaches that are incorrect. What's not incorrect is to draw an energy bar chart. I know that I have an oscillating spring. A spring should automatically tell you bar chart. So let's do that. Let's just do a bar chart for object P and the spring together. And let's start the bar chart at equilibrium. And let's end the bar chart at the max displacement. Max displacement, by definition, is the amplitude. We have 2 forms of energy we can have here. We can have kinetic energy and we can have spring potential energy. Kinetic energy will occur if the object is moving. Spring potential energy will occur if the spring is stretched or compressed. So the kinetic energy at equilibrium exists because the object is moving. So let's just put 3 bars there for the heck of it. At the equilibrium position, by definition, the spring is neither stretched nor compressed. So spring potential energy is 0. Work done by an external force. Well, the only external forces acting are gravity and the normal force, and they are both acting perpendicular to the direction of motion. They do no work. The spring force is part of the system, so that doesn't do work done by an external force, and we get 0. At the maximum displacement, the thing has stopped moving. So the kinetic energy is 0. Therefore, the kinetic energy converts to spring potential energy. We can say that the kinetic energy at the equilibrium position becomes spring potential energy at the maximum displacement. So what happens when the collision occurs? Well, whatever happens to the kinetic energy is also going to happen to the spring potential energy. And since the spring potential energy is 1/2 kx squared, where that's the amplitude, then whatever happens to the kinetic energy determines what the maximum displacement is. Since kinetic energy is 1/2 mv squared, we can write that, where that's the speed at the equilibrium position, and that is the maximum displacement. Okay, this is all correct, but let's show you the 3 common wrong answers that come from this. The first is, we know that we're looking for the amplitude, and since the amplitude is directly proportional to the mass and the mass increases, mass is in the numerator here, so bigger mass means bigger amplitude. That's not right. I get that all the time. That's not correct. Why not? Because this assumes, this would be correct if everything else stayed the same. The spring constant doesn't change, but the speed at the equilibrium position does change when I drop a block on there. So That's not correct. Let's try again. Now let's go through that. We know that to find the amplitude, we know the spring constant doesn't change. It's a property of a spring. We know that the mass increases by dropping the block Q on top. And we know that that is going to decrease the speed at the equilibrium position by conservation of momentum. So since one goes up, one goes down, that's an inverse relationship. These effects cancel. And X is unchanged. That's still wrong. Just because one variable goes up and the other variable goes down doesn't mean that the net effect is to not have a change. What if the mass doubled and the speed divided by 3? We have no idea. Okay, well, let's try this again. We know the mass goes up, but we know the speed goes down. But since speed is squared, then it has a bigger effect. So V goes down, so kinetic energy goes down and amplitude goes down. That's still incomplete. This assumes, this reasoning does, that whatever factor the mass changes by, the velocity changes by the same factor, such that this squared means that, say, doubling the mass would reduce the speed by 4 times. We don't have any evidence for that yet. It's not true that just because two things are multiplied together that the squared term dominates. It's true if the factor of change for both variables is the same, but we have no evidence of that. So what can we do? What can we do? Well, 3 things we can do. Let's talk about 3 things we can do. Firstly, we can approach with momentum conservation, since we know that the kinetic energy at equilibrium becomes potential energy, spring potential energy at the max displacement. Whatever happens to the kinetic energy at equilibrium determines what happens to the spring potential energy. The amplitude will decrease if the kinetic energy at equilibrium decreased, the spring potential energy, and thus the amplitude will increase if the kinetic energy increased. So let's find what happens to the kinetic energy at equilibrium. Well, let's do a momentum conservation problem. Let's have block P and block Q initially with speed, we'll call it V1. So the total momentum is m v1 plus 0 because Q has no speed. And that equals the total momentum after the collision, which is 3m, the total mass, times whatever this V2 is. So V2 equals 1/3 of V1. Therefore, kinetic energy is 1/2 mv squared. So initially, you got 1/2 mv1 squared. And then right after collision, the mass is tripled. The speed is that. There we go. So it turns out that the kinetic energy was cut by 1/3. Therefore, we can say that since the kinetic energy at equilibrium is smaller, that leads to less spring potential energy at maximum displacement and less amplitude. That is a correct answer. How could we do that more simply without going through that big conservation of momentum problem? Because you're only going to have 15 minutes to solve this problem. Well, let's consider that the conservation of momentum again. Total momentum is conserved. That is the momentum of block P plus the momentum of block Q before collision equals the momentum of block P plus the momentum of block Q after collision. And we know that Q had no momentum before the collision, and these guys stuck together. So the momentum of block P is equal to the momentum of block PQ combined after the collision. Well, what happens to the kinetic energy then? A formula for kinetic energy that is absolutely equivalent to 1/2 mv squared. It's not on the equation sheet, but I like to know this because it's easy when you know about momentum. Kinetic energy is p squared over 2m, where p is momentum. If you just multiply that out, mass times speed, it works out to 1/2 mv squared. But the point is, I can do this by saying the total momentum stayed the same of the PQ object system. The mass of the system increased, therefore the kinetic energy decreased. Since the kinetic energy decreased, that was converted to spring potential energy. Therefore, the spring potential energy decreased. Since that depends on amplitude, the amplitude must have decreased as well. That is fully correct. All right. Final way to think about this is with the definition of an elastic and inelastic collision. What kind of collision do we have? Well, we don't have an elastic collision. Collisions for which objects stick together cannot be elastic. And what does elastic mean? Elastic doesn't have to do with momentum conservation. Momentum is conserved in all collisions, always. But mechanical energy is only conserved in elastic collisions. In this case, the collision is not elastic, therefore mechanical energy was not conserved. So let us consider the system of P, Q, and the spring right before the collision and just after, right before and right after the collision. Well, we have some kinetic energy. Remember, we had 3 bars. I'm going to keep to that because block P was moving. There was no spring potential energy. Right after the collision, we're still at the x equals 0 mark. There is still no spring potential energy. But the collision was not elastic. There's no work done by external forces on the PQ system, but there is a conversion to internal energy. Where did the kinetic energy go? Mechanical energy wasn't conserved because this was not an elastic collision. Therefore, we must have less mechanical energy. Where did that bar of energy go? Well, it went into internal energy. Thermal energy, if you like when you rub your hands together and they get warm. That's what this internal energy means. So we know that the kinetic energy after the collision was less than it would have been if we just had block P. Therefore, we have kinetic energy converting to spring potential energy, but we have less kinetic energy in this collision, which was inelastic. We have less kinetic energy, so we have less spring potential energy. So less spring potential energy leads to less amplitude. That's the way I think of this, but any of these last 3 correct approaches is, well, correct. What's next? Experimental evidence. Now, I'm going to actually do this. Let me put this big so you can see me. I'm going to have this going, and I'm going to drop this 500-gram mass onto the cart when the cart is right at its equilibrium position. This is a 500-gram mass. This is 250-gram masses. So this is P and this is Q. I'm going to make sure I drop right at the equilibrium position. And I don't even have to do the iPad here, although I think I will record just so you can see it. You're going to see that the amplitude decreases. Try it again. Drop from a lower height this time. One more time. There we go. The amplitude was much smaller and it came off the track. When I did this before, I was getting it to stay on the track every time. And then it's derailed most of the times. There we go. Didn't derail that time. And we get a much smaller amplitude. So you can see that my reasoning was correct. The amplitude drops. So now, this is a paragraph response question. Let's talk about how to grade the paragraph response question. In this particular rubric, you can look it up. This was 2018 problem 5. You got 1 point for the correct answer in part A, that the square root of 3 was the ratio of the periods. Okay, that's easy. You just had to have the answer. But let's go through here. The correct answer doesn't matter. What matters is, firstly, these first 2 points, do we somehow recognize that the post-collision speed has decreased, either by applying conservation of momentum or by stating the collision is elastic? Well, we talked about that. We get 1 point then for saying not just that the speed decreased after the collision, but that we have less kinetic energy at the equilibrium position. That's the 3rd point in the paragraph. Then the next 2 points in the paragraph are talking about the energy conversion from equilibrium to maximum displacement. 1 point for basically that energy bar chart and explaining it, saying the kinetic energy of the blocks after collision equals the maximum potential energy of the spring. Or just talking about total mechanical energy. And then finally, some recognition of the fact that the maximum potential energy is where the maximum amplitude occurs. That's what amplitude is, recognizing what amplitude means here. That's 5 points. The 6th point is the paragraph point. For a logical, relevant, and internally consistent argument that addresses the required argument or question asked and follows the guidelines described in the published requirements for paragraph length response. Oi, yap, 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 yap. That just basically means, did you write a paragraph? And if so, was it on topic and logically consistent? Whether it's right or wrong, was it on topic and logically consistent? That's all we care about. So let's apply this rubric to the final reasoning that I gave you here. Let's say that Anthony is grading this right now. And Anthony says that he looks through here. And he says, well, we didn't apply conservation of momentum, but we did say that the collision is elastic. That's 2 points. We did do this bar chart to say that the kinetic energy converts to spring potential energy. And we recognize that that's the amplitude. Okay, so that should be 6 points, right? No, Anthony, that's not right. You're not grading this right. The question asks for a paragraph. And a paragraph means a series of sentences that are strung together. And a sentence has a subject and a verb. I only see 1 sentence in this whole response. It says collision is elastic. That's a subject and a verb. So I can look at that and I can give the 2 points here where it said for stating or implying that stating that the collision is inelastic. I can give those 2 points. The rest, there's no sentences. Even if the mathematics or the diagrams are all right, there are no sentences here, so I'm not reading them. A paragraph means a paragraph. But you say a paragraph is something you do in English class. All right, so let's write it this way. Might want to screenshot this because I ain't going to read the whole thing to you. I'm not making this up, really. I graded a paragraph problem, not this one. I graded the 2015 paragraph problem. And just think about a reader's reaction to this. We are professionals. We are going to find whether you have earned the points or not. But we don't need you to repeat the prompt 3 times. We don't need you to go into tremendous detail. A paragraph response, in my mind, should be about 4 to 6 sentences long. If you're going longer than that, who cares? This is not what your English teacher taught you to write. This is not something that you should be worried about. Well, wait, what if I don't say something? I might lose a point. Don't think about losing a point. If you do get 5 out of 6 points here, that's still a 5. Just tell me what you think is important in 4 to 6 sentences. Don't worry about, oh my gosh, my teacher might take off a point. It's not about that. It's just about communicating your reasoning. And this doesn't help us. I'd suggest if you want to see Just Google strong bad English paper. It's fantastic. 2.5-minute video showing you basically what not to do, and it's really funny. So don't do this. It makes me crazy. I will read this because I'm a professional, but if it's 4:30 in the afternoon and I know that I'm off in half an hour and I see this, I just go, ah. But your English teacher taught you that when you write a paragraph, you need to give an introduction sentence, like that one that says, there are many and various reasons that the new amplitude is less than the old amplitude. Your teacher taught you that you have to use motivation for the audience. You need to hook the audience and make them want to read this. Your audience has to read this. They're hooked. You should develop characters and you should make the audience be part of your world. So perhaps we should put this in the world of Bertha and Edna, and Bertha has been captured by the evil pirate, Larry. This is Larry the pirate. Larry has captured Bertha and taken Bertha to his lair. Bertha, I want to know the location of all the pickles. I'm not a pickle. Why would I know anything about pickles? Bertha says. And Larry says, I know you know. I know there's a shelf of pickles in your house. You got to tell me where they are. I'm not a pickle, and I don't know where any other elephants are. I'm going to get you. I'm going to move this cart back and forth, and it's going to bop you in the trunk as you get closer, Bond villain style. Closer and closer. Come on, spill the beans, Bertha. Tell me. No, I won't. Help me, Edna. And here comes Edna to the rescue. Edna recognizes that if she jumps on the cart at the equilibrium point, then it's an inelastic collision, and she will reduce the amplitude because she will reduce the speed at the equilibrium point. And since the kinetic energy will be reduced, that will translate to a maximum potential energy that's smaller and a smaller amplitude. So when she drops on there, the amplitude's smaller and Bertha's trunk doesn't get bopped. Foiled again. If you write that, I will be amused. You also notice that if you write it right, you probably got all 6 of the paragraph points. I'm not interested in Edna and Bertha fan fiction during the reading. If you want to write that and send it to me, oh my gosh, it would be a lot of fun. But that's not going to help you on the reading. I can't say, ooh, +1, cool story. It's not a story. It's a paragraph. I want you to tell me as concisely as possible what physics principles apply and how they apply. 4 to 6 sentences of logical explanation. Very simply, you could say, like Edna did, during the inelastic collision, the kinetic energy is reduced right at the equilibrium position. Since that kinetic energy translates to spring potential energy, the spring potential energy is reduced at its maximum displacement. And that's what an amplitude is, the maximum displacement. The amplitude is smaller. That's it. That's all you need. All right. Do we have time for, yes, we do have time for one more thing here. If you have any questions, stories, or comments, at Jacobs Physics is the way to go, and I will answer those. But I want to do one more thing for you guys. Some good reaction to this last time. Look at this, screenshot it. And once again, I want you to answer these questions. Pause the video. Yes, I mean it. Pause the video and answer these questions. Don't start it again until you have answered these questions to the best of your ability. I'm waiting. Now I'm back because you have already paused the video and answered these questions. And now I will answer them. I want you to take a pen and I want you to mark whether they're right or wrong. If you have a question, tweet me at Jacobs Physics to see whether I would have marked it right or wrong. How do you determine an object's direction of motion from a velocity time graph? Whether the graph is above or below the horizontal axis. That's it. Under what conditions is angular momentum conserved? No net external torque. Linear momentum is conserved when there's no net external force. Angular momentum is conserved when there's no net external torque. A system's kinetic energy decreases by 100 joules and potential energy increases with no internal energy change. What was the net work on the system, positive, negative, or 0? Well, let me just do a quick energy bar chart. The kinetic energy decreases by 100 joules. Let's do it better here. Here, I'll do it on a sheet of paper. It says the kinetic energy decreases by 100 joules. So there's 100 joules. There's the decrease of 100 joules. Potential energy increases by 75 joules. Was the net work on the system positive, negative, or zero? Well, we write bars plus bars equal bars. 4 plus question mark equals 3. Question mark is -1. So we need -1 joule or -1 bar of external work. So the net work on the system was negative. 2 forces are experienced by an object. 3 newtons to the right, 4 newtons down. What is the magnitude and direction of the net force? Well, the net force is given by the Pythagorean sum of these, so that would be 5 newtons. If you said that the direction was just down and to the right, that's not good enough. We need to somehow indicate that I find that angle by saying, I don't know, tangent of the angle is 4 newtons over 3 newtons. If you do that out on a calculator, which you're not going to have to do for this particular 2020 AP Physics exam, you can find that that's, I don't know, 53 degrees below the horizontal. It doesn't matter as long as you told me how to find that angle. If you use sine instead of tangent or cosine, that's fine too. But I do need you to understand that you can find the precise angle of that force. What's wrong with the free body diagram of a wheel rolling without slipping? Well, early in the year, I would say there's nothing wrong with this. There are 3 forces: the friction force, the force of the surface there, the normal force, the force of the surface, and mg, the force of the earth. But on an AP exam, if you are asked to draw the arrows on the free body diagram starting at the point of application of the force, well, a weight applies at the center of mass of the object. So that's correct. But the friction force should be here. The point of contact is where that force is applied, and that's right there. Similarly, the normal force is applied at the point of contact, so that would be a better free body diagram for FF and FN. Number F, under what conditions is the rotational inertia of an object not given by mr squared? When we have an extended or complicated object, let's say for a rod or for a disk rotating around itself. Anything that's not a point object. What's a point object, you ask? Several have asked on Twitter. A point object can be assumed to be a point object when the size of the object is small relative to the distance to the axis of rotation. If I go to my rotating platform here, rotating platform is like this. If I have a little thing on the edge here, this thing is maybe 3 centimeters wide, and it's maybe 8 centimeters to the center here. Well, that's small. This is a small thing compared to the distance to the axis of rotation. So this is a point object. Let's go back to the fundamentals. What is the horizontal acceleration of a projectile? 0. Ball is held at rest 1.5 meters above the table, a little higher than I can reach. The table is a meter above the ground. I remove the table, but I keep the ball where it is. By how much has the potential energy of the ball-Earth system changed? The answer is it hasn't. And the reason it hasn't is because the value mgh has not changed. But wait a second, isn't h the height above the lowest point? Yes. And didn't we change that h when we moved the table out from underneath? We didn't. Because before we start a problem, we have to define where is h equals 0? Where is the location of the lowest point that's possible to reach? So if I define that as the table, then when I took the table away, I still had a distance above where the table was, above our h equals 0 point of 1.5 meters. Okay, what if I use the ground as my h equals 0? Then when I remove the table, it doesn't matter. I'm still the same distance above the ground of 2.5 meters. Since the object didn't move up or down, the object could not have changed its gravitational potential energy. And standard kinematics equations for displacement, delta x equals v naught t plus 1/2 at squared. That's valid anytime that acceleration is constant, which is most of the time. And then the expression for change in angular momentum. Yes, I know change in angular momentum is final minus initial momentum. That's what a change means. But we can say that change in angular momentum is also equal to net torque times time interval. This is the impulse momentum theorem written for rotational motion. All right, the time has come, the walrus said. To talk of many things, I have 17 notifications on @JacobsPhysics. If you would like to ask a question, @JacobsPhysics, and Brad Williams will answer some of them, and I will answer many of these. Could I use the equation for the period of the spring to determine the answer to part B, says Lovely Butterfly. The answer to part B is the one where we're asking, well, what happens to the amplitude? Well, what's the equation for the period of a spring? There's the equation for the period of a spring. Notice that, excuse me, notice that the period of the spring is independent of the amplitude. It doesn't matter how much mass is on there or what the period is. The amplitude is not contained in that equation, so that's not going to work. That's why we have to use energy conservation to get at an amplitude. Interesting. And oh, wow, Brad Williams recognizes the Strong Bad reference. I really do encourage you to Google Strong Bad English paper, and you will be amused for the rest of the afternoon. Let's see, Liliana asks, can you re-explain how I conceptually knew that kinetic energy was converted to internal energy and spring potential energy? Yes, I was doing a bar chart for the two object and the spring system. Let's see if I can find this here. There we go. Both object P and Q and the spring. So object P was moving beforehand, object Q was not. So we had some kinetic energy beforehand. Just after collision, we know that we still had movement. But since the problem says the objects stuck together, that is by definition an inelastic collision. And if we go with our facts about elasticity of collision, which I had earlier, and I can't find them on this desk here. Oh, here we go. Anytime a collision for which objects stick together, the collision cannot be elastic. That means the mechanical energy must decrease after collision compared to before collision. In that case, the mechanical energy was just the kinetic energy right at the collision time. So I had to lose kinetic energy. That's the definition of an inelastic collision. Well, where did that energy go? Well, it's not mechanical energy, so it doesn't convert to spring energy or to any sort of potential energy. That energy has to become internal energy. That's what an inelastic collision means. An elastic collision means that the total mechanical energy doesn't change and that any kinetic energy lost has to be gained in some form of potential energy. Thank you for asking, Liliana. I hope that helped. Next. Oh, where did I get P squared equal? Kinetic energy is P squared over 2m. Brad Williams answered that. I just know that because kinetic energy is 1/2 mv squared, and I'm not on the switch camera so you can see. There you go. That's how I knew that. It's not something to memorize unless you want to. I devote 2 brain cells to that, just like I devote 2 brain cells to the fact that room temperature is about 1/40th of an EV. Don't ask me how I know that. And that there are about pi times 10 to the 7th seconds in a year. That's just something I know. Don't ask me why I know it or how I know it or whether it matters. Okay, we have time for 1 or 2 more. Blah, 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 blah. Shout out. Oh, I can do my shout outs. Shout out to Mrs. Gaeta from Suffern High School in Suffern, New Jersey. Soph says she is a wonderful physics teacher. I have a shout out to Brian Lau's physics teacher. Her name is Ms. Luneski from Marriott's Ridge High School in Marriottsville, Maryland. And a big one to 4-year-old Danny, who is watching with physics teacher Deb, who is Danny's mom. And they watch early in the morning, and Danny enjoys the show. I always think that we should have plush toys made of Edna, Bertha, and Anthony just for the purposes of letting little Danny have something to play with. All right, so that's enough for today. If you have more questions, go to @JacobsPhysics, and I will be happy to answer those. I will be on. Give me like 5 or 10 minutes to end the show and close out the Zoom. And then I will sit on Twitter for another half hour or so and answer all your questions. We will be here all week. I will note that tomorrow we will be covering 2017 problem 2. This is a static friction experiment. And I will be discussing this in the context both of an experimental problem, but also in the context of what sorts of things could we ask this year when the problem is not exclusively experimental. Don't worry, we're going to talk about all this. The rest of the week, I will be on Wednesday talking about a qualitative quantitative translation from 2017. Josh will be here on Thursday the 30th. He will be talking about problem 4 on the 2017 exams with two different ramps. And then I'll be back Friday to close out the review sessions, and that will be problem 1 from 2016, the famous qualitative quantitative translation about the bumpy track. Yes, Josh and I will be with you next week, noon Eastern every day. We'll have more details to come about what exactly that will entail during exam prep week. But for now, we will be with you each day. Please work on this problem for tomorrow. No spoilers. So if you want to know how you did on this one, don't bother tweeting me because I'm going to say no spoilers. You got to watch the show. If you want if you want our input on a problem that we've done previously or on a problem that we haven't done, feel free to tweet your response. And if I can get to it, I can't get to every one of the 170,000 people who are taking this exam. But if I have a chance, I will tweet back at you and tell you what you did right and wrong. Happy to help. So in a moment, I'm going to put up a slide where you can click to subscribe from the AP Physics channel. You can click to go to our playlist. You can click to go to all of our other, or go to the next episode. You can click to anything you want. But for now, for my friends Bertha, Edna, and Anthony, this is Greg Jacobs saying so long, everybody. Say goodnight, Edna.